Chapter 5.1, exercises 39 through 44 and 51 to 56. Section 5.1 is the part of our book that deals with the use of trigonometric identities, which we're going to use to solve some equations here and simplify some expressions. Here we have the expression cosine squared x plus 2 cosine x plus 1. I hope you recognize that this is what we call a quadratic expression. We call this a quadratic, abbreviate quadratic trinomial. And for a quadratic trinomial, we try to write a quadratic trinomial as a factor of two linear binomials, which I'm going to write down here. But to find out what goes in these parentheses, we're going to use what I call box method, which if you're a little rusty with factoring, using the box method for quadratic trinomials can be helpful. In the upper left corner of the box, we put in our first term, which is cosine squared x. That's our quadratic term. In the lower right, we put in our linear term, which is plus 1. And what are the factors of cosine squared x? We have cosine x and then cosine x. What are the factors of 1? Well, they're going to be simply 1 times 1 or negative 1 times negative 1. And here, since we have plus 2 cosine x, we're going to try plus 1 on the top, plus 1 on the side. 1 times cosine x is cosine x, and cosine x times 1 is cosine x. And combining these like terms in the middle, we're going to get 2 cosine x. When we write this out, we're going to get cosine squared x plus 2 cosine x plus 1. And so we can write in our factors are going to be simply quantity cosine x plus 1 times quantity cosine x plus 1, which we can write as quantity cosine x plus 1. And since these two these linear, I like linear actually because I wouldn't call them linear, but they're in the form of a linear binomial, we can write as a square. So quantity cosine x plus 1 squared. Next, problem 41. Okay, we have kind of a form that I guess we could almost call this quadratic trinomial, except here we have cosine squared x and sine x. So they're not the same. But we can try to use our Pythagorean identity, and the kind of the parent Pythagorean identity is sine squared theta plus cosine squared theta is equal to 1. And we're going to try to replace this cosine squared theta, and to do that, what I'm going to do is we're going to try to replace this whole thing here. See if we can do that. If we subtract cosine squared theta from both sides of this equation, okay, we have cosine squared theta minus cosine squared theta canceled equals 0. So we get sine squared theta equals 1 minus cosine squared theta. And here we see 1 minus cosine squared theta, so we can replace 1 minus cosine squared theta with sine squared theta. So we're going to get equal 1 minus 2 sine x plus, I'm going to put sine squared x. And we can rewrite this expression here in standard form by putting sine, the quadratic term up front, sine squared x minus 2 sine x plus 1. And getting out our box like we did last time, we put the first term in the upper left corner, which is sine squared x. And lower right, we put plus 1. And the factors of sine squared x are sine x and sine x. And the factors of 1 are negative 1 times negative 1, or positive 1 times positive 1. But here we have minus 2 sine x, so negative 1 probably is going to work. Negative 1 times sine x is minus or negative sine x. And negative 1 times sine x over here in the lower left is going to be negative sine x. And if we add these two together here, we're going to get minus 2 sine x. And of course we have plus 1 and sine squared x here. So this is going to work out. So rewriting as a product of two factors, we're going to have sine x, quantity sine x, minus 1 times quantity sine x minus 1, which we can rewrite as quantity sine x minus 1 squared. So this is going to be our answer to problem number 41. Now, going to problem, next odd number problem, problem number 43. Okay, we have cosine x minus 2 sine squared x plus 1. What I'm going to do is you pull out our Pythagorean identity again, sine squared theta plus cosine squared theta is equal to 1. And if we solve for sine squared theta, we can subtract cosine squared theta from both sides of this equation. We have a cancellation on the left, so we get sine squared theta equals 1 minus cosine squared theta. And we can replace sine squared theta in our original expression here with this right here. And so to do that, we get cosine x minus 2, and replacing 1 minus cosine squared theta, we put 1 minus cosine squared x in the place of sine squared x plus 1. And distributing, let me just bring cosine x down, distributing 2 to inside parentheses, we're going to have minus 2, and then minus negative 2 times negative cosine squared x is going to be plus 2 cosine squared x plus 1. And combining like terms, we're going to have cosine x, and negative 2 plus 1 is going to be minus 1 plus 2 cosine squared x. And rearranging this quadratic trinomial in standard form, we have 2 cosine squared x plus cosine x minus 1. And now, using our factoring, like we've done before, quadratic trinomial, this time on our upper left, we have our quadratic term, which is going to be 2 cosine squared x. And lower right, we have minus 1. So on the top, our factors of 2 cosine squared x are 2 cosine x. And on the top left, we have cosine x. And our factors of negative 1 are going to be negative 1 times 1. So if we put negative 1 here on the top and 1 here on the side, we're going to get negative 1 times cosine x could be minus or negative cosine x, and 2 cosine x times 1 is going to be 2 cosine x. And if we add these two middle terms together, we're going to get 2 cosine x minus cosine x equals cosine x, which is what we wanted. That's what we have originally, right? Cosine x. That's right over here. We had originally. So that's going to work. So this is going to be equal to quantity, open parentheses, 2 cosine x minus 1 2 cosine x minus 1 times quantity cosine x plus 1. And there we have it. Okay, so that's going to be some factoring problems. The next one we're going to go to is exercise 51-56. Find all solutions to the equation in the interval from 0 to 2 pi. You do not need a calculator. Okay. Well, we're going to use factoring as much as we can here. And we look for a common factor between these two terms as 2 cosine x sine x and minus cosine x. So our common factor is going to be cosine x between these two terms. So we can rewrite this equation as cosine x times quantity 2 sine x, and what times cosine x equals negative cosine x? Well, that's going to be minus 1. And that is all equal to 0. And using principles of solving equations, we can set each of these factors equal to 0. So we have cosine x equals 0, and we have 2 sine x minus 1 is equal to 0. And we can solve the 1 on the right by adding 1 to both sides. Cancellation, 2 sine x equals 1, and dividing by 2, we have sine x equals 1/2. So now we can go ahead and identify on our unit circle, which I'm sketching here in the upper right, places where cosine x is 0 and sine x is 1/2. Let's take the cosine x. Cosine has to do with the x-coordinate, and the x-coordinate is going to be 0 all along this y-axis. So if we go to the very top, we have a cosine of 0 at pi over 2 at the top of the unit circle, and at the very bottom also at 3 pi over 2. So those would be two of our solutions. Next, we're looking for where sine x is 1/2. Well, I'm going to draw horizontal. At pi over 6, our cosine is square root of 3 over 2, but our sine is 1/2. And the same, if we go across to the quadrant 2, to the left, at this angle here, which is 5 pi over 6, we also have a sine of 1/2. So we can write our solutions as x, we'll write the set notation, and just by convention, you try to start with the lowest value first, lowest number. So we're going to have pi over 6 is one of our solutions, comma, next we go around the circle to pi over 2. Going around the unit circle, we have 5 pi over 6. And our last solution we have here is at the bottom of the unit circle, which is 3 pi over 2. So that's our set notation version of our answer for problem number 51. All right, let's look at our next odd number problem, which is problem number 53. We have the tangent x, sine squared x equals tangent x. In factoring, it's usually helpful to have one side of the equation equal to 0, and the easiest way to do that would be to subtract tangent x from both sides of this equation. So subtracting tangent x from both sides of the equation, we cancel on the right, and left we have tangent x sine squared x minus tangent x is equal to 0. And we look for a common factor between these two terms, and we find that in tangent x. Well, tangent x times what equals tangent x sine squared x? So that's going to be simply sine squared x. And we're going to have what times tangent x equals minus tangent x? So that's going to be minus 1. That's equal to 0. And what we have is for the sine squared x minus 1, it may not be readily apparent to you, but that is a form of a difference of squares. So tangent x we're just going to bring down, but we can rewrite this sine squared x minus 1 as a product of two binomials, which are going to be sine x minus 1 times quantity sine x plus 1. So if we set these expressions, each one of them equals 0, if we have tangent x is equal to 0, right? Or if we have sine x minus 1 is equal to 0, we have sine x plus 1 equals 0. And solving, we have sine x equals 1, and we have sine x equals negative 1. Well, what we have here is equation. Let's see where this happens. Okay, tangent x is going to be equal to 0 at because at sine over cosine is equal to tangent, right? So tangent is going to be equal to 0 at x equals 0 and at pi. Now sine x equals 1 at where? Up here at pi over 2, and sine x equals negative 1 down here at 3 pi over 2. But what is the value of cosine at pi over 2 and 3 pi over 2? So cosine of pi over 2 is equal to 0. And cosine of 3 pi over 2 is also equal to 0. Well, where the cosine is equal to 0, remember tangent is sine over cosine, so the function will be undefined at pi over 2 and at 3 pi over 2. So the only possible solutions we have are going to be these we've already found in this first equation for tangent, which is x is either equal to 0 or pi. All right, problem number 55. Tangent squared x equals 3. This is not in a trinomial form, and where you have a quadratic and a constant, we can solve usually using a square root method. So if we take the square root of both sides of this equation, I'm just going to draw this on the original, we get tangent x is equal to plus or minus the square root of 3. Plus or minus square root of 3. Well, let's find where the square root of 3 is. If we go to the unit circle, and if we take square root of 3, it's going to be, sine is have to be bigger than cosine. So if we go up to 60 degrees here, which is going to be pi over 3, at pi over 3, our cosine value is going to be 1/2. The sine value is going to be square root of 3 over 2. And if we continue around, 180 degrees opposite, we're going to have, let's see, that's going to be 2 pi over 3 here. This is going to be 4 pi over 3. We're going to have sine value of our cosine value of negative 1/2 and sine value of negative square root of 3 over 2. If we go over here to 2 pi over 3, we have our cosine is going to be negative 1/2. Our sine is going to be positive square root of 3 over 2. And if we go down over here to the fourth quadrant, we're going to have 5 pi over 3. And for that, we're going to have a cosine value of 1/2, but a sine value of negative square root of 3 over 2. So just figuring these out, on the right one, if we have tangent, okay, if we say tangent pi over 3 equals a sine over cosine, which is going to be square root of 3 over 2 over cosine, which is 1/2. This is going to be equal to square root of 3 over 2 times 2 over 1. So we cancel, we get square root of 3, which is going to be plus square root of 3. If we go down to quadrant 3, we're going to get negative square root of 3 over 2 divided by negative 1/2, and we will get, so 4 pi over 3 is an answer. If we go to tangent, we try to take the tangent of 2 pi over 3, we have sine, which is square root of 3 over 2, divided by negative 1/2. And that's going to be square root of 3 over 2 times negative 2 over 1, or canceling, we're going to get negative square root of 3. And that's going to be the same for 5 pi over 3. So in this case, x is equal to each one of these points identified. Pi over 3, 2 pi over 3. Coming around to quadrant 3, we have 4 pi over 3. And in quadrant 4, we have 5 pi over 3. Anyway, use of identities, trigonometric identities, to solve equations. I hope this has been helpful to you, and I say good luck, and thank you for viewing.